and welcome back. So let's talk about some of the essential concepts of chemistry that you'll need to know for a basic biology course.
So here's an outline of some of the items we're going to look over. First, I'm going to introduce you to the idea of matter. More specifically, I'm going to introduce you to the atom. Okay? Atoms have a basic structure and they behave a certain way, and that behavior results in what we call chemical bonding or reactions. We'll look at some ideas such as the periodic table and how it tells us about atomic number, mass, the idea of isotopes, and a little bit about the bonding and bond types you'll need to know for this class. We'll also look later on in other lectures, other lectures coming up, at some of the ideas such as the properties of water, super important to biology. Also solutions, buffers, and pH. For most of you, this is usually about chapter 2 in any of the textbooks you have. So hopefully that'll help align you. So this is it. This is the basic building blocks of matter. This is called the atom, right? So the atom, well, let's turn my pen on. There it is. This is atom like this. Oh, I always do delta. There it is, atom, like this. This is the fundamental unit of matter. And so as such, it has a couple of little, what we call subatomic particles. We're going to look at those subatomic particles. First, let's look at the regions. This little part in the center is what we call the nucleus. Now, this is an idea we'll see a few times in this class. The nucleus means the center of something, where a lot of the activity is, right? It's a center of a lot of operations. Okay, within the nucleus are going to be two particles, protons and neutrons. So protons are positively charged. And over here, these are going to be neutrons. Now they have a neutral charge. Something that's important about them is they're also about supposedly relatively the same size as our protons. Okay? So the last bit is this little one over here. This is the electron. So the electron is going to be the negatively charged particle. It's very small. So the electron moves in funny ways. It's attracted to the protons, but it only stays in what we call like this little cloud or valence. And even though we see it kind of in these ring structures, it's actually buzzing around like a bead. You never know where it is at any moment, right? Electrons are going to give us our reaction for the most part. They tend to be the ones that like to interact with other adjacent atoms. We have two or more atoms linked up together, we're going to have a molecule, and those are really important building blocks of life. All right, well, now you know about the atom. So things to remember: the positive charge of those protons and the negative charge of these electrons act like a magnet. Okay, and you remember how magnets at school were. We'll get back talking about that in a little bit. This is the periodic table of elements. So the periodic table of elements is kind of like a taxonomy for elements, right? Atoms of a specific species, right? So chemists have organized them based primarily on what their atomic numbers are, okay? And that's grouped them into some great and interesting categories, like the metals can be found in certain regions and the gases can be found in certain regions, cool stuff like that. Well, for the most part, we just need you to know a few things. Number one, what the element symbol is going to mean, right? So the element symbol for carbon is C. And so what that tells us is that this is going to be carbon. Easy enough. C, carbon. All right, that fits together. What about this one down here? Fe. What could that even be? Well, here's something interesting. It's actually iron, right, for ferrous. So sometimes we look at different types of root words, like the Latinization of the root word. And that's where we get our element symbol, okay? So that's one way to kind of just be aware that that's something that can surprise folks. Another thing is going to be the atomic number. That's how many protons you have in the nucleus. Important stuff, right? The mass number is how many protons and neutrons. Remember, they have a neutral charge you have in the nucleus. Now, say you have a carbon with, instead of a mass number of 12, it has 13. that means that you have still, the atomic number of 6, so 6 protons, but you have 7 neutrons. It brings you into a new category. That is now an isotope. It's also known as carbon-13, right? So that's an isotope. Okay, let's look at some other features of them. So, right, key things to remember: atomic number, element symbol, mass number. Remember, some of these can change up on you. Mass number, remember, is neutrons plus protons, and the idea of the isotope, right? Okay, so I just wanted to review a few essentials here. So we have electrons. Oops. Let's review them with a pen and not my mover. There we go. Electrons, negatively charged. This is going to be the part of the atom that is typically active during bonding. The outer shell electrons are going to determine chemical behavior, and we'll talk about what that means in just a sec. Also, remember the nucleus has neutrons and protons, but does not have electrons. A neutron has no charge, and it is important in determining isotopes, just like on the previous slide. A proton has a positive charge and tells us what kind of element we're dealing with. It gives us the atomic number. Okay, so let's talk about something else. There it is. Okay, let's talk about this idea of the outer electron shell, okay, and valences generally. So here's how it works. Every single atom has at least, a space for 2 electrons. It doesn't mean they have to have 2 electrons, it means they have space in that first ring. Then you have additional rings, okay? And each one of those additional rings can hold much more. They can hold up to 8, okay? It doesn't mean they have 8, but it does mean they can hold up to 8. Let's change the color on that one. There we go. Those are some red ones. Okay. So remember, the inner shell or inner valence will always be able to hold at least 2. And the outer one likes to hold 8. Now, it doesn't mean they always have them, but that's what they like to hold. That's their happy place. They're always trying to look for more electrons to fill their valences. And so sometimes that works against the idea of how many protons they have in the nucleus. This is what results in reactions, different types of reactions. Electron energy levels. Now let's look at how those electrons and those empty seats on the valences can result in reactions. Let's keep in mind a few things. Chemical properties of an atom are based on the arrangements of its electrons. Okay, so that means we're talking about the shells and how many seats they have to fill. We're going to look at 3 main types of bonds: ionic bonds, covalent bonds, of which there are 2 types to review: nonpolar and polar, and hydrogen bonds. But it's really important that we start with this idea of magnetism. It kind of helps conceptually understand what we're doing here with this type of chemistry. Remember these? Remember these magnets when you were a kid, maybe in elementary school? Well, at least when I was. The teacher would get tired or bored or something and pull out this big bucket of magnets and take us out to the playground, and we would try to pull out all of the iron from the sand, and then we'd put it on construction paper and look at all the different designs it would make. And usually they would look like this, these tiny little grains of magnetic metal. And we'd be playing with the magnets in other ways. And some of those ways would be like if you had a north-facing pole and a south-facing pole, they would attract. Opposites attract. You've heard it, but it happened in magnets before it happened anywhere else. The other one is similar repel. So the like ends of the pole will push away, and no matter how hard you tried to jam those south poles together, they just slipped right past each other. That's really important because remember, positively charged and negatively charged, right? Negative and positive charges, they work the same way, but that's what we describe them as when they work on an atom. Now let's look again at that atom. Okay, so we have negatively charged, negatively charged electrons over here. And now we have some positively charged protons over here. So that means there's an attractive force. That's important. Let's talk about some of the ways that those attractive forces can result in bond types, or the ways that different types of Molecules can be made or arranged, or even destroyed.
Wow, look what happened. We had a transfer of electrons. It looks like big old chlorine over here just stole one from sodium. So let's take a look at this. Just kind of the details are important here. Let's do some counting. Number one, sodium. The inside still has 11 positive subatomic particles, 11 protons. But the rings, if you count them all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, still only have 10 electrons, because one jumped. And so we have a 10 electron charge. That means 11 positive plus 10 negative gives us an overall charge of positive 1. This means we have a 1 positive or positively charged atom. It's an ion. An ion is a charged particle or molecule. So also, we didn't just get one out of the deal, we got two. So chlorine, let's add it up, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 now electrons. Overall charge of 18, now that we stole one, electrons, but we still only have 17 protons in the middle. So we do the same math. 17 positive plus 18 negative gives us negative 1, right? We have an overall negatively charged ion by 1. That's the basics of how you get an ion. And this is the salt example. We're going to come back to this idea a lot during. So we did a lot. We found out a little bit more about how we can transfer electrons, but that's like not everything. There's more. So now, remember when we talked about those magnets and how you had those two polar ends and you'd have one that was positively charged and you have one that's negatively charged, and like maybe the negative end of another one be attracted to the positive end, right? And so that's how we would get these magnets to stick together, like that attractive force. Well, now we basically have created two magnets, okay? One magnet over here is a positively charged end, and the other magnet over here is a negatively charged end. So guess what they start doing? They start hanging out. Now it's a weak bond. I mean, let's not forget what just happened here. Chlorine just literally stole something from sodium. Okay, that's not a real good start to any type of relationship. So they're really only attracted to each other because sodium still needs just enough negativity to balance out its positive subatomic particles, and chlorine's kind of just along for the ride. It's a bigger molecule, so sodium's going to follow it around, or bigger atom, so sodium's going to follow it around. So now these two are kind of stuck together, just like a magnet. That results in what we call an ionic bond. So they still need each other. They still kind of hang out together. It's not a super healthy relationship, but they're still stuck together because those positive and negative charges attract. Ionic bonds.
Now, a more stable type of bond that we're going to look at next is called the covalent bond.
This is an example of a covalent bond. It's much more stable. It's a strong bond. It's not like an ionic bond. We'll see later easy ways that things such as just water and other polar molecules can break something as simple as an ionic bond. But covalent bonds are different. They actually make water. So here's what it looks like, a piece of water that's being made. A covalent bond is the sharing of electrons, right? So they are sharing electrons. They're not stealing from each other. They kind of have a joint custody arrangement. So what happens here is this is oxygen. Oxygen is 8 protons, but it usually only has about 6 as a result. Remember, we have the inner valence shell that has 2 electrons, so we only have 1, 2, 3, 4, 5, 6 electrons on the outer shell as a result, right? Remember, we got, here's the inside valence with 1, 2, so it makes sense. So when it comes to oxygen, it's kind of what we call an electron thief. It's really well known for stealing electrons from other molecules. But hydrogen's a little different. Hydrogen has 1 proton in the center, 1, and has 1 electron on the valence. So what ends up happening is hydrogens become attracted to these oxygens, and they don't have their electrons stolen as much as they start to share them. So part of the time, here, let me see if I can do it. You got to think about how electrons move, which is they can be anywhere at any time. So it's this cloud, right? So here's electrons that are being shared. So they can be anywhere at any time. So this is one of the ways that we can get away with sharing an electron. So the sharing of electron results in something really special, the covalently bonded molecule. In this case, we have our water molecule that we've just made, right? Super stuff. So there's a couple of ways you can represent it. You can represent it like this, showing all the electrons in big circles, or sometimes you can do a stick model like this. There's a couple ways that molecules are represented when we talk about them in academic texts or textbooks. So just be aware that that's something you might see if you have some other resources that you're going to use for studying on your own, or even the ones that I provide, because it's kind of all over the board. But if you get lost, make sure to reach out. I can help.
Now let's talk about hydrogen bonds. The last kind.
Hydrogen bonding is really neat. It's actually more of an attractive force if you think about it. So in this case, we took our water that we just made, since we can make water. This is a space filling model also. So remember I showed you there's different ways to represent molecules? This is one of them. See how it looks like almost a three-dimensional shape? Right, it's still water, just like we looked at before. It's just represented differently. This kind of shows how the arrangement of the oxygen and the hydrogens operate in space, right? So this is how they look in space. So let's think about some things. Number one, remember we have an oxygen on one side, and we have hydrogens over here. So if you'll notice, all of these kind of look like Mickey Mouse, right? So you got ears up here, and you've got, you know, the bigger molecule down here, which would look like the face. So here's how it works. Oxygen still has 8 of those protons. It's a lot. And those little hydrogens, they still only have 1 proton, right? So that's an issue. And what it does is it means the electrons want to spend most of their time over here by the oxygen. Okay, they want to spend most of their time over here. A little bit over here, but not so much. It means that what we're looking at is an imbalance of charges, right? So here you go. If all the electrons are on this side most of the time, this is going to be a more negatively charged side. And if over here the electrons are almost never there, it means these two positive charges are kind of the greater power. So it's more positively charged on that side. So then oxygen itself, even though it's a covalently bonded molecule, because of this unequal sharing, because the electrons want to be over by this positive nucleus that big oxygen has, we have a disequilibrium of charges, right? Oops. Some better arrows for you guys. Okay. And it himself becomes a magnet of sorts. Okay? So now let's look over here at this picture. Okay, so here's what happens when you cluster them up together. So think about it this way. First off, all of these little water molecules are magnets now. All right, so that's okay. But know what happens when you throw a bunch of magnets in together? Well, they start flipping around like fish in a stream. And what they're trying to do is orient themselves, specifically. Okay? Here's what they're trying to do. they're trying to align their positive ends, right, to a negative end. That's what they're trying to do. So we start getting these arrangements in this case, right? This is a hydrogen type bond. So even though no electrons are being shared or taken away or jumping or moving over, they're still causing attractive forces. They're still causing a bond, a type of bond. We're going to examine this one a lot in an upcoming lecture, which talks about the chemical properties of water and why water is so unique and so special and so essential to biology and life on Earth. All right.
So that's it for these essential concepts in chemistry. If you have any questions, please feel free to reach out. Otherwise, I hope it helps.